Click the bell icon to get latest videos from Ekeeda.
Hello friends, in today's session we are going to study the types of hard water. Whenever we talk about hard water, there are two types of hard water. The first is temporary hard water and the second is permanent hard water. Temporary hard water is the water which can be easily softened. That means that hard water can be converted into soft water very easily by certain physical processes like boiling. But when it comes to permanent hard water, we need to do chemical reactions and chemical processes to convert that hard water into soft water. In today's session, we'll study both of these in detail. Types of hardness. There are two types of hardness. The first is temporary hardness. Now this temporary hardness is also known as carbonate hardness, is also known as alkaline hardness. So temporary, carbonate and alkaline, all of them refer to one type of hardness, and that is temporary hardness. Now this temporary hardness is caused by carbonates and bicarbonates of calcium and magnesium salts. Calcium is Ca, magnesium is Mg. So whenever I have calcium carbonate or calcium bicarbonate or magnesium carbonate or magnesium bicarbonate, both of them will refer to my temporary hardness. The second type of hardness is known as permanent hardness. Now this permanent hardness has another name, which is non-carbonate or non-alkaline hardness. When we talk about non-carbonate hardness, that means that the salts of calcium and magnesium will not be carbonates, will not be bicarbonates. They will be everything apart from carbonates and bicarbonates, and every other salt means the sulfides of it, the chlorides of it, and many other oxides. All the sulfides, chlorides, oxides, etc. come under the category of permanent hardness. All the carbonates and bicarbonates come under the category of temporary hardness. All the sulfides, chlorides and oxides come under permanent hardness, whereas all the carbonates and bicarbonates come under temporary hardness. Let us study temporary hardness in detail. Temporary or carbonate or alkaline hardness. It is defined as the hardness due to carbonates, hydroxides, bicarbonates of calcium, magnesium and other metals. So whenever we have any metal with us, we have commonly calcium and magnesium, but apart from calcium and magnesium, we can have ferrous, that is iron. We can also have aluminium, but that ferrous and aluminium should have either in the hydroxide format or the carbonate format or the bicarbonate format. All of these form temporary hardness. Temporary hardness is mostly removed by mere boiling of water. Either we boil the water or we expose it to some amount of heat, and we make sure that temporary hardness is removed only by physical processes. There is no need of any kind of chemical reaction to take place to remove the temporary hardness. Only physical processes can help removing the temporary hardness and convert that hard water into soft water, where bicarbonates are decomposed, producing insoluble carbonates or hydroxides. So if I have a soluble impurity in the water, for example, I have water, a sample of water which is hard, and that hard water contains temporary hardness and not permanent hardness. So if it contains temporary hardness, that means it must be containing either bicarbonates or carbonates of calcium and magnesium. We cannot see the impurities which are present in the water because they are soluble in water, they are completely resolved in water. By boiling, we do is a certain kind of chemical reaction. Only by boiling, these soluble impurities get converted into something which are precipitates, and precipitates are nothing but insoluble in water. So the first step we do is we take the water, we boil it, and after boiling it, we let it cool down. After cooling it down, we will see certain precipitates which are formed on the surface of the water sample. Now these precipitates are nothing but the insoluble impurities. We can easily filter out these impurities, and after filtering it out, we'll get pure water or soft water. Let us see them in the form of reactions. So the first one over here is CaHCO3 twice. This entire HCO3 is twice. This is known as calcium bicarbonate, and we are providing heat to it. So when we provide heat to it, it gets converted into CaCO3, and this is a downward arrow. Downward arrow shows precipitate. So this CaHCO3 twice was a soluble impurity in water, but CaCO3 is insoluble because it is a precipitate. Now this CaCO3 is nothing but calcium carbonate, plus H2O and plus CO2 gas. So whenever we are heating water which contains calcium bicarbonate impurity, in the product side I can see two arrows. The first arrow is a precipitate arrow and the second arrow is in the form of a volatile arrow. Volatile arrow means it is in the gaseous form, it will just escape out of the system into the atmosphere. That means the first impurity precipitates down, the second impurity escapes out, and what remains is pure water. Thus, in my output, I will get soft water. Let us see what exactly happens over here. We have CaHCO3 twice. So, I have one calcium on the reactant side. On the product side also, I have one calcium. Now, this entire HCO3 is twice. That means my hydrogen will be twice, my carbon will be twice, and my oxygen will be 3 into 2, which is 6 times. Now, how did this 3 into 2 come? This O is 3 inside the bracket. We have O3 inside the bracket and that entire bracket is twice. That means this will be 3 twice. O3 is twice and therefore the entire amount of oxygen on my reactant side will be 3 into 2, that is 6. Let us see the calculation of hydrogen on the reactant side. On reactant side hydrogen is 2. On the product side also I have hydrogen as 2. The number of carbons on my reactant side are 2 over here. On the product side also I have 1 over here and the second one is over here. That means the carbon is also balanced. Finally, coming to the oxygen, this is O3 which is twice. That means oxygen is 6 on my reactant side. Over here, if you all see, I have 3 plus 1, 4 plus 2, 6. That means the oxygen is also balanced. This entire reaction is my balanced reaction. So whenever I have calcium bicarbonate, this Ca and this CO3 comes together. Then this H2 and another O comes together forming H2O and the remaining substances form CO2. This is the best way of converting my hard water into soft water because we are just applying heat to it and we are getting a precipitate and a volatile form, and whatever remains is just pure water. Now this is for my calcium bicarbonate. We can do the exact same reaction for my magnesium bicarbonate. So over here I had calcium bicarbonate. We are doing this for magnesium bicarbonate over here. So this is MgHCO3 twice. Instead of Ca, we are having Mg over here. We are doing the same thing. We are applying heat to it and we get MgOH twice. Again, when you see MgOH twice, it's a precipitate. This is magnesium hydroxide and 2 CO2 gaseous. That means this is volatile. That means one will be a precipitate, one will be a volatile. That means this entire impurity can be broken down into two things. This soluble impurity in the water can be broken down into two things. The first thing is the insoluble precipitate in the water and the second thing is the volatile form of CO2 which escapes out of the system. That means that impurity will not be there at all once that water is filtered out. Let us see the balancing of this reaction. We have 1 mg on the reactant side. We have 1 mg on the product side. Now since it is a bicarbonate, we have HCO3 twice. That means this entire HCO3 is twice. This entire bracket is twice. Therefore the hydrogen will be 2, carbon will also be 2 and I have O3 which is twice. That means this entire O3 is twice. This will be 3 into 2, that is 6. My oxygen will be 6. Let us see the balancing over here. Hydrogen is 2 on the reactant side, hydrogen is 2 on the product side. Now from where did we get 2? This is OH and this entire bracket is twice. That means each and every component in the bracket will be twice. Since hydrogen is one of the component in the bracket, that hydrogen will also be twice. So this is H2. Then we have carbon. We have 2 carbons on the reactant side. We have 2 carbons on the product side as well. Over here my carbon is twice. Over here also I have 2 carbons. Finally, moving down to oxygen, we have O3 twice. That means oxygen overall is 6. 3 into 2, 6. On my product side, I have 2 oxygens over here. Since oxygen is a part of this bracket, I have 2 oxygens over here. And we have 2 CO2. Now this 2 and this 2 will multiply forming a 4. So I have 4 plus 2, 6 on the product side as well. Therefore, this is my entire balanced reaction where we take a soluble magnesium bicarbonate, heat it and convert it into an insoluble magnesium hydroxide, which is a precipitate, plus CO2, which is volatile, and then we filter out that to get soft water. So over here we have another example. We have CaHCO3 twice or MgHCO3 twice. So either you can take the CaHCO3 twice example or you can take the MgHCO3 twice example. We have taken both of them together because both of them work in the same manner. We'll see each of them individually as well. First, let us take CaHCO3 twice. This is a bicarbonate of calcium. This is calcium bicarbonate where we have CaHCO3 and the entire HCO3 is twice. Plus 2 times C17H35C double bond OONA. Now this entire thing is known as sodium salt of stearic acid, and this is nothing but a soluble soap over here. So what we are doing is we are taking the impurity and we are taking a sodium salt of stearic acid, that is a soluble soap, but we are taking it 2 times over here. What happens over here is this Ca has a valency of 2. Ca always has a valency of 2. Even Mg has a valency of 2. Because it has a valency of 2, it needed 2 of HCO3. Now, if we are removing HCO3 out of it, it will need something else which will also have a valency of 2. That means over here we have taken C17H35C double bond OO. This entire stuff we'll take and we will attach this stuff to Ca, or we'll make Ca get attached to this. So this is C17H35C double bond O, and this entire thing is twice. Over here on the reactant side we have taken twice because calcium has a valency of 2. Calcium needs to satisfy its 2 bonds, and that is the reason why this entire thing we'll take it as twice, and then we'll make a bond with Ca. This is known as calcium salt of stearic acid. This is known as calcium salt of stearic acid. Now let us see what all is remaining over here. Over here we have Na which is remaining, and we have HCO3 twice remaining. Again Na is also twice because 2 is to the entire thing. So Na is also remaining, that is 2 Nas are remaining and 2 HCO3s are remaining. So they will form nothing but 2 NaHCO3, which is a sodium bicarbonate. Now this calcium salt of stearic acid is insoluble and will precipitate out. So this is my entire reaction with calcium. Let us see the balancing over here. We have 1 calcium on the reactant side, 1 calcium over here on the product side. This entire C17H35C double bond OONA, this entire thing will divide it into 2 parts. The first part will be C17H35C double bond OO. This entire thing will be first part, and this first part is 2 on the reactant side. This entire part is copied down over here, C17H35COO, and this part is also 2 on the product side. That means this entire part is balanced. Now let us see what all is remaining. We have HCO3 twice and we have Na twice. That means 2 Nas on my reactant side. I have 2 Nas on the product side, and 2 HCO3s on the reactant side. I have 2 HCO3s on the product side as well. That means this entire reaction is my balanced reaction where we convert a bicarbonate of calcium into a stearic salt of calcium with the help of sodium salts of stearic acid. This entire reaction can be done with magnesium as well. Over here, instead of calcium, we have magnesium. So we have MgHCO3 twice. This is nothing but my magnesium bicarbonate. This is the soluble impurity which is present in the water. Sodium salt of stearic acid, also known as soluble soap. This entire soluble soap is added to my MgHCO3 twice. And over here what happens is, instead of calcium, the Mg will get attached to it. That means this Mg over here goes and gets attached to C17H35C double bond OO. So over here I have Mg C17H35C double bond OO. It is important for us to remember that Mg has a valency of 2, and that is the reason why on the reactant side also we have HCO3, which is twice, because the valency of Mg is 2. Thus, to satisfy its valency in the product side also, we'll have to give 2 things to it, and thus we give C17H35C double bond OO, which is 2 on the reactant side, will also form 2 on the product side. This is nothing but my magnesium salt of stearic acid, and whatever remains over here is 2 of Na and HCO3, which is also 2, and they form 2 NaHCO3. If we see the balancing of the entire reaction, I have 1 mg on the reactant side, I have 1 mg on the product side. I have 2 C17H35C double bond OO on the reactant side. I have 2 C17H35C double bond OO on the product side as well. Finally, what remains is 2 sodiums, which is over here, 2 Na, and we have HCO3, which is also 2. So this is also HCO3, which is 2, that is sodium bicarbonate. This is how we convert the impurities of calcium and magnesium, which are soluble in water, into the stearic acid format, which are insoluble in water, with the help of soluble soap. The next reaction over here is with CaCl2 or MgCl2. The same reaction can be done with CaSO4 or MgSO4. First, let us take an example of CaCl2. CaCl2 is nothing but a calcium chloride. Now again over here, calcium has a valency of 2. We have 2 C17H35C double bond OONA. Again, we divide this into 2 parts over here. We take this as the first part, whereas we have C17H35C double bond OO. And this will go and attach itself to calcium over here. So this will again form C17H35COO twice of calcium. This is nothing but calcium salt of stearic acid. And whatever remains over here is, we have Cl remaining over here and we have 2 Nas remaining over here. That will form 2 NaCl. This is the same reaction. This was for bicarbonates, but this is for chlorides. Again over here the same thing is happening. The calcium is getting attached to this part of the salt, which forms a stearic acid of calcium. And whatever is remaining, that is 2 Nas are remaining over here and 2 Cls are remaining over here, are forming 2 NaCl. If we see the balancing will be Ca, that is 1 Ca on my reactant side, 1 Ca on my product side, 2 C17H35C double bond OO on the reactant side. We have 2 C17H35C double bond OO on the product side. We have 2 chlorines on the reactant side, 2 chlorines on the reactant side, 2 sodiums on the reactant side and 2 sodiums on the product side. That means this entire reaction for the chloride is balanced. The same reaction can be done for magnesium chlorides as well. We have MgCl2. It is the same reaction, but over here instead of Ca we will have Mg. That means this Cl2 and this 2Na will form the same byproduct of 2 NaCl, and this Mg over here will go and attach itself to C17H35COO, which is over here. So 2 C17H35COO are on the reactant side, which gets attached to the Mg. So over here I have magnesium with C17H35COO, which is twice. The entire same reaction can be done for the sulfates or the sulfides of CaSO4 or MgSO4. The same thing will happen, but over here instead of NaCl we will have Na2SO4. Now how did we get Na2SO4? It is important for us to understand that SO4 itself has a valency of -2. Ca has a valency of +2, and thus one SO4 is enough for one Ca, because 2 bonds of SO4 will go and attach itself to 2 bonds of Ca. The same thing happens for Mg. Over here we have MgSO4. SO4 itself has a valency of -2. Mg has a valency of +2. That means 2 bonds of SO4 will go and get attached to 2 bonds of Mg. This entire thing over here is CaSO4. We do not need 2 SO4s over here. Over here we have MgSO4. We do not need 2 SO4s over here. We needed 2 chlorines because chlorine had a valency of 1. To satisfy calcium we needed 2 chlorines. Over here also chlorine has a valency of 1. To satisfy magnesium we needed 2 chlorines. But over here SO4 itself has a valency of 2, and thus we do not take 2 SO4s, we just take 1 SO4. So we have CaSO4 or MgSO4. Now this CaSO4, let's first focus on CaSO4, goes and gets attacked by 2 C17H35C double bond OONA. Again remember, this 2 will remain as it is, nothing is being changed, because we will need this 2 to satisfy the valency of Ca also and SO4 also. This calcium will go and get attached to the first part of this, that is C17H35COO, forming C17H35COO, which is twice and Ca. Now whatever is remaining will form the byproduct. Over here we have 2 Nas remaining, and we have one SO4 remaining. These two NAs will need one SO4. Why? Because SO4 itself has a valency of -2. To satisfy the valency of SO4, that is -2, we will need two NAs because NAs have a valency of +1. So +1 for one SO4 valency and +1 for another SO4 valency, forming Na2SO4. The next is MgSO4. Again, it is the same thing, but instead of calcium, we have Mg now. We have MgSO4 plus 2C17H35COONA. Again, over here, SO4 has a valency of 2 minus, Mg has a valency of 2 plus. For this 2 plus valency, we will take 2 of C17H35COO. This entire thing gets attached to Mg, forming magnesium salt of stearic acid. This Mg is now attached over here to C17H35COO, which is twice, and whatever remains will become my byproduct. What is remaining over here is SO4. What is remaining over here is 2Na. So both of them combine and form Na2SO4. The Ca or Mg carbonates or hydroxides thus formed, being almost insoluble, are deposited at the crust or the scale at the bottom of the vessel, while CO2 escapes in the air. Whenever we have seen the reaction, we have a water container. We take the water, which is temporarily hard, and we boil it. Two things are formed. One is a precipitate, second is a volatile substance. Volatile substance is anything which will just escape out of the system. Over here, what is our system? Our system is the container containing water. So, either CO2 escapes out or we have a precipitate formed which is at the bottom. So whenever we boil the temporary hard water, by mere boiling of it, the CO2 will escape out and the precipitate will remain at the bottom. After filtering that off, whatever we get is pure soft water. The next thing we are going to do is permanent or non-carbonate or non-alkaline hardness. It is due to the presence of dissolved chlorides, sulfates, and nitrates of calcium, magnesium, iron, and any other metal. Apart from iron, the other metals can be aluminium as well. So over here, we will take calcium, magnesium, iron, and aluminium, and we will not have carbonates or bicarbonates of them. We will instead have chlorides, sulfates, or nitrates. And that is the reason why the name of this hardness is known as non-carbonate hardness, because we do not have carbonates or bicarbonates over here. Permanent hardness is not destroyed on boiling. It requires special chemical treatment for removal of hardness causing salts, such as internal conditioning or external conditioning. That means we have two methods over here, internal method and external method. But both of these methods are not physical methods, they are chemical processes. That means we'll have to put in certain kind of chemical reactions to it and make sure that these ion exchange happen. That means the impurities, the ions of the impurities are taken away by other chemicals and form a precipitate down. The softening methods used on large scale in industries are lime soda method, zeolite perlmuttite method, and ion exchange method. Now these are the most important three methods which are used to convert permanent hard water into soft water. Temporary hard water can be converted into soft water by mere boiling of it. But for permanent hard water, we will need chemical reactions to happen, and these chemical reactions happen with the help of either lime soda method or zeolite perlmuttite method or ion exchange method. Now these are the three reagents over here which are being used. That means they will have big machineries. These machineries will have chemicals inside it, and when you pass your hard water through the chemicals inside it, the chemicals will try reacting with the hard water, try converting the ions of the impurities into something else which can be formed as a precipitate and settle down. We'll study all these processes in detail in the later sessions. So here in today's session, we studied the types of hardness. We concluded there are two types of hardness. The first is temporary hardness, the second is permanent hardness. We saw what kinds of substances and impurities are there in temporary hardness and how to remove them. We also saw the substances which are there in permanent hardness and the methods to remove them as well. Thank you so much for watching this video. Stay tuned to Ekeeda and subscribe to Ekeeda.